Hey guys, this is Professor Janacek, and I just want to work through some examples of finding antiderivatives. Let's start with example 1 here. We've got the integral, or antiderivative, of 3x to the 5th plus 2 minus 5x times the square root of x dx. So what we're going to do here, first thing, not real crazy about working with radicals, so let's rewrite that as a rational exponent. So we have the integral of 3x to the 5th plus 2 minus 5x to the 1/2 power dx. So the idea behind finding antiderivatives or integrating is we're going to undo the derivative. So I'm going to do kind of the opposite of what we did for derivatives. With derivatives, we had the power rule where we took the exponent, multiplied it to the coefficient, and then subtracted 1. I'm going to do that whole process. I'm going to do the opposite of that process in reverse order. So what we end up having is 3 times x to the 5 plus 1. Instead of subtracting 1, I'm now adding 1. And instead of multiplying by that, I'm going to divide by that exponent. If you remember, taking the derivative of just an x gave us a constant, so it turns out if I want to take the antiderivative of 2, we simply get 2x. And then for the 5x to the 1/2, again, we're going to use kind of the opposite of the power rule. So we have 5x to the 1/2 plus 1 in the exponent, and then we divide that by 1/2 plus 1. Don't forget that we do have a plus 0 in the back of every integrand, and the antiderivative of 0 is a constant, so we have to have that plus c out there. Now, if we simplify all this stuff, we end up with, let's see, that's going to be 3 over 6, which reduces to 1/2 x to the 6th plus 2x minus, now be careful with this, we have 1/2 plus 1 in the denominator, that's 3/2. But now we, as the coefficient in the numerator is 5, divided by 3/2 gives us 10/3. But then we still have x to the 3/2 power plus our constant c. Now let's take a look at example 2. We're going to integrate 4x to the 19th minus 5x to the negative 8 over x squared dx. I think the first thing that we should do here is to go ahead and simplify that integrand, make it as simple as possible to work with. I noticed that 4x to the 19th over x squared is 4x to the 17th, and 5x to the negative 8th over x squared, that gives us minus 5x to the negative 10th. And now again, we're going to basically use the opposite of the power rule. So we end up with 4x to the 17 plus 1 over 17 plus 1 minus 5x to the negative 10 plus 1 over negative 10 plus 1. Don't forget about that arbitrary constant out there. Antiderivative of 0 is a constant, so we've got that plus c. And now we'll just simplify. 4 over 18 will reduce to 2/9, x to the 18th. And then minus 5 over negative 10 plus 1, that will simplify to a plus 5/9, x to the negative 9th, and then we still have our constant there in the back. Looking at example 3, if we integrate z squared plus 1 times 2z minus 5 dz, notice my variable here throughout is a z, not an x. I think to make this one a little easier to work, I'll start by just multiplying out that integrand. So that gives us the integral of 2z cubed minus 5z squared plus 2z minus 5. Taking the Antiderivative of that, we get 2z to the 3 plus 1 over 3 plus 1 minus 5z to the 2 plus 1 over 2 plus 1 plus 2z to the 1 plus 1 divided by 1 plus 1 minus 5z plus our arbitrary constant. Now this all simplifies. 2 over 4 is 1/2 z to the 4th minus 5/3 z cubed. 2 over 2 gives us just 1 z squared minus 5z plus our constant. Now, example 4 looks interesting. We're going to integrate secant squared x dx. What we need to remember here is that the derivative of what function results in secant squared. It turns out that's the tangent function if we remember our derivative rules. Therefore, the integral of secant squared x dx is simply the tangent of x. But don't forget, we have that arbitrary constant. Finally, let's integrate dx over x. Now, you can work it in this format, but I think it's much easier to see if we rewrite this as the integral of 1 over x dx. Notice I'm just going to move that dx off to the side so I can work with 1 over x. Now I simply have to recall, what do we take the derivative of, which gives us 1 over x? Well, it turns out that that's the natural log of the absolute value of x. Thus, the integral of 1 over x dx is the natural log of the absolute value of x. Don't forget that arbitrary constant in the back. And there you go. Enjoy!